this video, we're going to talk about the cosine values and sine values of every one of these angle increments around the unit circle. In order to do that, we kind of need to go back and talk about a little geometry first. So I'm going to go talk about some geometry. The only angles that you can find the exact sine and cosines of are those that are in increments of 45 degrees and or 30, 60. The reason behind that is because when you create a 45-degree angle, triangle, 45, 45, 90, geometrically, or, go back here, on the unit circle, when I drop this down, and I've got my 90, and I say, okay, I'm cutting off pi over 4 radians, 5 degrees. And again, I've got my 45, 45, 90 created in there. And the reason we can work with this one and get its exact sines, cosines, tangents, etc. is because it's half of a square. So those legs right there are the same. So I'm going to go back to the geometry of it. Go right here and right here. And you say, well, those are the same, and we're talking about sine and cosine. If you remember your SOHCAHTOA, I'm only going to write the SOHCAH. We're talking about the ratio for sine of the opposite to the hypotenuse. For cosine, we're talking about the ratio of the adjacent to the hypotenuse. So because they're ratios, I mean, I'm just going to generically call this x, x. And with the 45, 45 being half a square, they're always the same. So with my Pythagorean theorem, I can kind of go figure out, well, what is this c over here always? I'll always have a side squared plus a side squared equals that hypotenuse squared, which gives me 2 of them. And when I take the square root, I'll get the hypotenuse. The square root of x squared is just x. So for the 45, 45, I always get this x root 2 right here, which means if this was 8, I'd have 8, I'd have 8 root 2. For the ease of working with it, because we're only going to be working with the ratios, again, the ratio of this side to this side is always x to x, which would be 1. So for the ease of working with it, I'm going to go back up here and erase it. And it doesn't really matter what I call these as long as they're the same, which means I'm just going to make u1 and u1. And again, this would be 1 times the square root of 2. So when I talk about the ratio or the sine of that 45-degree angle or the cosine, again, I'm talking about the ratio of the opposite side to the hypotenuse, which will always be in a ratio of 1 to root 2. So we say the sine of our 45 degrees is opposite over hypotenuse, which is 1 to root 2. And when we rationalize that denominator, we get root 2 over 2. Likewise, cosine of an angle is the ratio of the adjacent to the hypotenuse, and the adjacent to the 45 degrees is 1. Hypotenuse still root 2, so they're the same. So for the 45, 45 degree triangle, we get sine and cosine. And again, it doesn't matter. Had I called these, I mean, even just 10, 10, 10 root 2, when I do the ratios, I'm still going to get the same thing. You can, if you don't believe me, I'll show it to you really quick. Had I just done 10 and then 10 right here for my sides, these cancel, and I still end up getting that same ratio. So with the 45, 45, I've got the sine of root 2 over 2 and the cosine of root 2 over 2. Now, likewise, in a similar fashion, I can talk about the 30-degree and 60-degree because that's created by cutting an equilateral triangle in half and doing the geometry of it here just so you can slice that down here. Take a look at it. Now, just for the ease of working with it, you can kind of notice that this side gets cut in half. So what I've got here is this length is always half of this length. And for the ease of working with it, those are in a ratio of 1 to 2. 1 to 2. Now, again, it's just for the ease of working with it that I'm calling it 1 to 2, so you can visualize it. It could be, I could have put a, 7 here and a 14 here, but because we're talking about ratios, it's going to reduce to 1 to 2 anyway. So I'm going to go put that on there. Now, if you take a look at this third side over here, I'm going to do it just with the numbers. I would say, well, a squared plus b squared, other leg squared, let's just call that a b here, equals c squared. And so I get b squared is equal to 4 minus 1, which is 3, and I get b root 3. So when I talk about the sine and cosine here, again, using that SOHCAHTOA concept, I'm not putting the toe on because we're not talking about tangent right now. Again, we've got our sine is opposite over hypotenuse, which is why that we say that the sine of 30 degrees is always a half. The ratio of the opposite to the hypotenuse is always going to be the ratio of 1 to 2. Now the cosine's different on this one. For cosine, we do adjacent over hypotenuse, which gives us root 3 over 2. So back to our picture here. You may have memorized in pre-calc or algebra 2, cosine's x, sine is y. This is true, but I kind of want to talk about why is that. Why is it that they tell you that the cosine of an angle is its x value on the unit circle only, and the sine is its y value? Let's talk about that for an instant here. I think I'll go to a clean page to show you that. Because it's the unit circle, unit meaning 1, my radius is 1. So when I talk about an angle here, let me just like that. Whoops. So I got the eraser on there. Go put an angle on here. I'm going to call that theta. This is 1. And then I'm talking about this point right here. This is x over and y up. Notice when I talk about the cosine of an angle, I take adjacent, and for the unit circle, the hypotenuse is always the radius, which is 1 here for the unit circle. So when I do the cosine and I do adjacent over hypotenuse, I just get x, which is why we say that the cosine of an angle is really its x value. Likewise, sine is opposite over adjacent, hypotenuse, so I'd have y over 1, which is y. So that's kind of why we're always taught that cosine's x and sine is y. And it has to do with the fact that we're on the unit circle here, so the hypotenuse technically is always going to be a 1. So, going back over here, I just proved to you a little while ago that the cosine of 45 degrees is equal to root 2 over 2, and we said the sine was the same thing, root 2 over 2. Really what that's telling you, this is the x, this is the y. So right here is root 2 over 2, root 2 over 2. And you can see it's the same amount to the right as it is up. That's why these are equal here. So every point represents cosine, sine. So we would say that the cosine of 45 degrees is root 2 over 2, sine is root 2 over 2. Well, what that also gives you then is if you were to flip this over to this one, it also gives us over here. They're exactly the same to the left and up. The only difference is the cosine would be negative and the sine would be positive because I'm going to the left and up, which is why we would say that the cosine of 3 pi over 4 is negative root 2 over 2, and the sine is positive root 2 over 2. Likewise, down in the third quadrant, they're both negative. So it'd be negative root 2 over 2, negative root 2 over 2. So if I were to ask you for the cosine of 5 pi over 4, you would say, well, it's the x value there, which is negative root 2 over 2. Moving over to quadrant 4 at that 45 degree, we've got an x value that's positive and a y value that's negative. So all of those. But really, if you just remember the 45, 45, they're both the same, and then flip, and then again flip over, and then flip. Negative for the x, negative for both, and then negative for the y. It's very helpful. Likewise, with the 30 degree, or pi over 6 radians, again, when we're talking about cosine and sine, I proved on the previous page when we did this that the sine was 1/2 and the cosine was root 3 over 2. What that does then is it gives you, again, this one over here, this one over here, and this one over here, because these are all the same, just changing of signs. So what that's going to do is, going over to quadrant 2, we've got our x negative and our y positive. Right here, they'd both be negative. And over here, we would have just down, or just a y negative. So again, you kind of get 4 for 1 on all of these. Last up, if we were to talk about the 60-degree angle, pi over 3 radians up here, I'm going to kind of go back a page so you can see it. If I were to do, that should have been 30 right there. If I were to do on here my 60-degree angle, you'll notice what happens is, go back to the geometry of it, when I do the sine of my 60 degrees, which is opposite over hypotenuse, here we go, I get opposite over hypotenuse, root 3 over 2. If I were to do the cosine of 60 degrees, I would do adjacent over hypotenuse, so adjacent would be 1, hypotenuse would be 2. Notice it just switches what happens with the 30 degrees, and conceptually it should make sense why that happens. It's because what's opposite the 60 degrees is adjacent to the 30 degrees. So those values just interchange. So back over to our circle here. Let's see if I've got another one. Well, I'll just use this one. If this is root 3 over 2 1/2, then this one just reverses. So again, really, what it all boils down to when you're all done is those special triangles, and we really don't want to memorize. So again, I'm going to give you a way that I do this without having to memorize. In my head, I keep in mind that the cosine is the x value, the sine of an angle is the y value. It gives me these endpoints very easily. So this is 1 to the right, 0 up, 0, 1, negative 1, 0, and 0, negative 1. So those are very easy to think about. If somebody said, what's the sine of pi over 2? Well, 1. What's the cosine of 3 pi over 2? Well, 0, the x value. So those endpoints are the first ones and the key ones to think about. For the other ones, I really just worry about this quadrant, and then I flip and flip and flip. The easiest thing to remember is that the pi over 4, the 45, 45, they're the same. Kind of like the half of a square, the sides are the same. And we show that they're root 2 over 2, root 2 over 2, which would give you, again, this one, and this one, just by changing a sign. For the pi over 6, I always just remember that the sine is a half, and then the cosine falls in nicely, and then I remember that this one, for the 60 degrees, they just interchange. Now, there are some other shortcuts that I've seen, some tricks, if you really don't understand where those are coming from with those special right triangles. There's some tricks that I'll show you, but I like to avoid the tricks, so I want you to work with this first. Again, now if we take all of these and flip them over the y-axis, what's going to happen is all of the x-coordinates are going to go negative. The y's will stay the same. So basically, it's just a reflection, which means over here would be negative 3 over half. I'd reflect this one over. It would be negative root 2 over 2. Positive root 2 over 2. And I'd flip that one over to be negative a half, positive. And again, now this flips over that way, and you just kind of keep flipping, keeping in mind what the signs are in every quadrant. Makes it very easy to create. Now I'm going to be out of time here, so you should practice that, and we'll have a more discussion about that in class too, but just practice that. The next video will be on a couple of tricks to use if you can't